All right. So what we have done till today. So this is the schematic diagram of a MOS transistor, right? So we have source, drain, body, and gate. We have 4 terminals. So let's see. I mean, since we're till today we're discussing about electrostatics. That means uh, uh, how means what is the relation between gate voltage and charge in the silicon, right? Here your source and drain. So basically, when I discuss about electrostatics, we're not talking about current. So your source and drain are grounded. Body is also grounded, and you are applying gate voltage. So if you apply positive gate voltage, if you apply gate voltage, so there will be charges in the substrate. So if you apply positive gate voltage, there will be negative charges in the substrate. If you apply negative gate voltage, there will be positive charges in the substrate, right? Um, so we had also derived this relationship, which is an important relationship. So the gate voltage. So whatever voltage you apply to the gate, some of this voltage drops in the oxide, your gate dielectric, and the rest drops in the silicon, right? And we are discussing this psi s is the drop in the silicon, and the psi s is the surface potential, right? So psi s is the surface potential. That means at this point, at the surface, at the interface, this is the psi s. So the voltage drop in the silicon is nothing but psi s minus the voltage, I mean voltage applied at the body. And in this case, since the body is grounded, the voltage applied across the silicon is voltage drop across silicon is psi s. So we had means done this, and we know that this is nothing but the semiconductor charge, whatever charge in the uh, plus is. So the Vox, the voltage drop in the oxide is nothing but is related to the charge in the silicon. Higher the charge in the silicon, then higher will be the voltage drop, right? So this charge in the silicon also we talked about. So we have a depletion charge, and also we have inversion charge. So this is the summation of both the charges plus psi s, right? So if I go ahead, so we have Vg. Vg is Qd by Cox, this plus Q inversion and divided by Cox plus psi s, right? And so we know what is Qd. So Qd is we had derived already in the last class. So we could write this as 2 epsilon Si Q times Na root over psi s, right? And similarly, Q inversion also we have derived, and this is 2 epsilon Kt, right? Just a moment. Q inversion 2 epsilon Kt Ni square by Na, right? E to the power Q psi s by 2 Kt. Right, so this is my this is the relationship for the inversion charge. So we know that inversion charge Q inversion is exponentially related to psi s, but the depletion charge has a root over psi s relationship, right? So basically, means we have also looked at the how the total charge in the silicon varies with psi s. So and and we had plotted that also. Let me quickly plot this one. So just quickly, because we have already done it. So we have QD and Q. So if you look at the depletion charge will go like this, and your inversion charge will go exponentially. So your total charge will somehow look like this, right? So total charge. So the total charge, if you see, so this will somehow uh, yeah, a little bit, right? So it could see, so it will go like this, right? So yeah, I'm talking, so this, so what I'm plotting here is QSI and psi s, right? And this point we call it this is 2 psi b, right? So this is where the inversion happens, right? So when your surface potential or potential drop in the silicon is equal to 2 psi b, right? So please keep it in mind, 2 psi b is the potential drop in the silicon, right? So when it becomes 2 psi b, then your transistor moves from depletion to inversion, right? And also we derived your, again let me write down. So Vg is Qd by Cox plus Q inversion divided by Cox plus Is. So from here also we also written down the threshold voltage equation. So threshold voltage, at the threshold voltage, so this will happen when the surface potential becomes 2 psi b, right? And this is nothing but Qd by Cox, because if you see at this point, I mean, so I also told you last time, so you'll see that Q inversion, if you calculate, so Q inversion is less than Q depletion. We could neglect Q inversion, so this will be 2 psi b. So this also you could write down 2 epsilon Si Q times Na divided by Cox root over 2 psi b plus 2 psi, right? So here you see, so once your device is fabricated, so basically your Na is fixed, your oxide thickness, your oxide capacitance is fixed, right? So here Cox is nothing but your Eox by epsilon ox by Tox, and epsilon ox, see epsilon ox is a permittivity, right? So we know for oxide, your dielectric constant relate into 10 to minus 14 farad per centimeter, right? So this right. So so once you fabricate your transistor also in a fixed technology, right? So when you talk about CMOS technology, for a fixed CMOS technology, so your oxide thickness is fixed and your Na is fixed, right? So basically this whole term, right? This is a constant. So I could also write down as plus 2 psi b, right? So this is your threshold voltage, right? So you see your threshold voltage is a function of Na and your oxide, right? So your threshold voltage is a function of your doping and oxide thickness. So if you so basically if you basically your Tox, right? So for a technology Tox is fixed, right? So you, most of you are using 180 nanometer CMOS technology. So for 180 nanometer CMOS technology, your Tox is fixed, right? We know that this is T3 nanometer, right? So Tox is fixed at 3 nanometer, right? So if you want to change the threshold voltage of the device, that you could change by changing the doping Na, right? So you could change the doping of the transistor or the doping of the substrate. By changing the substrate doping, you could change the threshold voltage. So this is from the equation. But if you look at the physical significance, why the threshold voltage depends on Na. So you see, if you look at this equation, so there are two things, right? Right. So you have N plus and P substrate and N plus. So, and we are talking about the doping at this region is Na, right? So if your Na, if your substrate doping is higher, if your Na is higher, then definitely to invert, because what is the condition for inversion? Inversion is number of electrons on the surface, right? Number of electrons on the surface equals the doping, right? So if the doping is high, that means you need to apply higher gate voltage, right? You need to apply higher gate voltage, right? So this is the kind of, so that's the reason your VTH is higher. Other reason is, so your barrier, right? So basically when you're talking about, because electrons are injected from source and drain to the channel, right? So there is a potential barrier between N plus and N plus P junction. So there is a potential barrier here, and that barrier is I mean, if a doping is high, because N plus is fixed, right? So N plus, this is very highly doped, maybe around 10 to 21 per centimeter cube. So, but if you increase your Na, if you increase your substrate doping, then that barrier is higher, right? So since the already this barrier is higher between the source and substrate junction, right? So you need to apply higher gate voltage for the electrons to be injected from N plus to means your source and drain to bottom, right? So this is, there are two things. One is your substrate doping is higher. That's why you need more number of electrons for inversion. That is one reason for why your VTH is higher. And second reason is your this, because your electrons are coming from the source and drain. Since the doping is higher, Na is higher, your barrier is already higher, so you have to apply more voltage. So that's the reason. So you have two terms here, right? Na is coming from psi b also here, and Na term here, right? So these are the two terms I was talking about now, right? Okay, and oxide thickness. So if you increase the oxide thickness, so your voltage drop in the oxide increases. So your voltage drop in the silicon reduces at the same, for the same gate voltage. Since the voltage drop in the silicon reduces, you need higher gate voltage to forward bias, means properly forward bias the body and your source and drain junctions, right? So that's why you need higher threshold voltage. Okay, so this thing is about um, threshold voltage, but please keep in mind, so this equation that we have derived, right, your threshold voltage, this equation that you have derived, that your threshold voltage is root over 2 epsilon s I q n a root over 2 psi b divided by a Cox plus 2 psi b, right? So this is for a ideal transistor, right? So this equation is for an ideal transistor, right? Ideal transistor, right? What do you mean by ideal transistor? So ideal transistor means when I'm talking about because let's say, so this is your gate dielectric, right? Your silicon dioxide, and this is your silicon. So um, right. So here, if you look at the interface, right? So we are not, because we are assuming that this interface is ideal, right? Your silicon dioxide silicon interface. So we are assuming that the silicon dioxide silicon interface is ideal, right? So, but in practical case, there are some, because what happens, right? So in the silicon wafer, so so this surface we have some dangling bonds, right? And the silicon, when you grow silicon oxide, the silicon oxide passivates some of the dangling bonds, right? But it didn't, it really does not and does not passivate all the dangling bonds, right? So there are some charges at the interface, right? So let's say this charge, I have, so this surface is not ideal, but I have some charges, let's say interface charge q interface, right? Right. So so in the practical case, you have some interface charges, right? And also your oxide, that silicon dioxide is not idle also, right? So there might be some charges inside silicon oxide, right? So let's start with, right, we have a interface charge. If you have a interface charge, have an interface charge of q in, right? Okay, so let's assume, I'm assuming, let's assume the q interface charge is negative, right? So if what do you mean by q interface is negative? So let's say I have some negative charges at the interface, right? So let's start with this, right? So if this interface charge is negative, then you see how do you start, right? Because if I'm applying some gate voltage here, right, right, and I know that I have so there will be some electric field, and let's say this electric field, right, and this displacement vector. So basically if I see, so there is a displacement vector, right? So let's say this is upper and lower, right? So upper is the displacement vector on top of the interface du, and displacement vector on the bottom of the interface is dl, right? So upper and lower, right? So if you go from the electrostatics point of view, right? So we could write down this displacement vector du, right, is your interface charge plus dl, right? So basically, if the displacement vector is from top to down, right? So it's displacement vector because this electric field is from top to down. So we could write this, right? So du is nothing but q interface plus dl, right? And dl, we know that this is nothing but q interface plus this is the q silicon, right? So means dl is nothing but q silicon, right? Okay, so now, and this du is nothing but epsilon ox times electric field. So this is q silicon. So electric field in the oxide is nothing but q interface charge plus q silicon divided by epsilon oxide. So if I go back to my equation, my that KVL that I always write, Vg equal to Vx plus Is, right? And this is nothing but times Tox plus Is. So, right? But here, so I could write down this Eox as Q interface plus Q silicon divided by epsilon ox Tox plus Is. So this becomes Q interface plus Q silicon divided by Cox plus Is, right? So your gate voltage becomes QSI by Cox, total charge in the silicon by Cox, plus Is, plus an additional term, right, is Q interface, right? So whatever charge I have at the interface divided by C oxide. But keep in mind, right, so Q int and QSI are similar. I mean, similar in the means same charge, right? Are similar. I mean, this is here I am assuming that this is negative, right? So your Q silicon is negative, right? Because this is NMOS, so your Q silicon is negative, and here I have assumed that Q int is negative, right? So from here also, if I want to write down the threshold voltage, your threshold voltage you could write down. So this is QD by Cox. So QD at this time will be 2 epsilon Si Q Na divided by Cox root over 2 psi b. Right? This is my QD when I'm calculating the threshold voltage. And your psi S potential drop in the silicon is 2 psi b and plus Q in by C oxide. Right? So so here I have added an extra term, right? So basically, if I have some negative charge at the interface, right? If my silicon is not ideal, my transistor is not ideal, I have some negative charge at the interface, your threshold voltage will increase, right? So so basically here, right? Because your threshold voltage will increase because there are some negative charges at the interface. So you could think it in another way. Since we have negative charges at the interface, right? So okay, so I have some negative charges at the interface. Let's say I have some negative charges at the interface, right? So some negative charges at the interface. So some of the field lines will terminate with these negative charges, right? So some of the field lines will lost, right? So that means I have applied gate voltage. There are field lines. Some of the field lines are not reaching silicon because I have some negative charges at the interface. They are terminating there, right? Since less number of field lines is reaching silicon, I have to apply more gate voltage to invert the surface, right? So you could think of in that way, right? This is why your threshold voltage will be higher if my Q interface charge is negative. But other way, if my interface charge is positive, right? If Q interface is positive, right? Let's say this is positive charge, right? Then your threshold voltage will be, you could write down, right? You could write down here. So if interface charge is positive, so this will be, right? So your threshold voltage will be lower, right? Why threshold voltage will be lower? Because if you see, if I have positive charge at the interface, right? So these positive charge at the interface will also induce some negative charges in the silicon, right? So the negative charges in the silicon is not only induced by the gate field, also by this positive charge at the interface, right? So since interface charges is also helping in inverting or in creating negative charges in the silicon, then your threshold voltage will be lower, right? So you could think of in that way, right? So for a practical silicon, I'll have this interface charges. So based on the sign of this interface charge, if this interface charge is positive, then my threshold voltage will be lower. If my interface charge is negative, your threshold voltage will be high. But in many cases, what will happen is, let's say, this is my um, silicon, um, right? Um, okay. So I might have charges somewhere here, right? Somewhere, let's say charges is not at the interface. I have some charges in the oxide, right? So, and let's say these charges are somewhere in the middle of the oxide, somewhere in the oxide, which, and this is called the fixed oxide charges, because uh, so what happens? These charges are created because of some vacancies in silicon dioxide, right? So so we have so in case of silicon dioxide, right? One silicon is bonded to different oxygen atoms, right? So if one bonding is not proper, then this will give rise to fixed oxide charge, right? So let's say this charge is fixed. Fixed means this is not moving, right? So these are located at that place, right? And let's say this is located at a place, at a place which is xf from the polysilicon interface, right? So this is my metal, right? So from the metal it is located at xf, and this will be automatically tox minus xf, right? So right. So in this case, if I ask you, okay, what will be the effect of this charge, this fixed charge on the threshold voltage? So what will be its effect, right? And assuming your fixed charge is negative, right? So what will be its effect? If this fixed charge QF is negative, right? So let's say, let me erase this and I'll put negative charges, right? So let's say I have negative charges somewhere located except below. Uh, so, right? Okay. So what will happen if I have some negative charge located at a position XF below metal? So how the threshold voltage will change? So anybody?
So drop across the oxide will increase
Okay. Okay. So why there will be more drop in the oxide?
because now there will be electric field inside the oxide also.
No, electric field तो पहले भी था, right?
But I'm imagining that some work will be done to move these charges.
No, these charges are fixed charges. They will not be moved, right? So they are fixed charges. So see, these charges are created because of some unbonded oxygen atoms, right? So these charges are fixed, right? So that's why I call it QF, right? Fixed charge, right? No, but you are going in the correct direction. So there will be some voltage drop in the oxide will change, right? But voltage drop in the oxide, see, voltage drop in the oxide is nothing but electric field into your oxide thickness, right? So there will be some change in the electric field, right? So because you have okay, so if you do our analysis in the similar way, right? So let's say I have my flux lines, right? So let's say this is du and this is dl, right? So I could write down this du is nothing but qf qf plus dr, sorry, dl, right, du equal to qf plus dl, right? And your dl, because the flux line means the lower of this qf, lower part of this QF is nothing but DEU minus QF, right? So because of this negative, okay, all right. So and here, see, this DL is nothing but your Q silicon, right? Because these flux lines is this DL, they are entering silicon, right? So this DL equal to Q silicon, right? And so basically, if you look at here, so the field in this part of oxide will be different than the field of this part of the oxide. And let's say this field is EU and this field is EL, right? So since there are some negative charges in the middle, let's say at some places in the oxide, so the electric field will not be constant, right? So electric field will change, right? So, and we'll have two electric fields, one on top of QF and on bottom of QF, right? Let's say this is EU and EL, right? Right. So, right. So, what is EL? So, okay. So if you look at EU, so EU is QF plus DL divided by epsilon ox, right? And EL is nothing but your QSI by epsilon ox, right? So this is the electric field, right? If this yeah, if okay, so now if I want to find the Vox, right, your Vox, the total voltage is your EU, right? So times XF, because this thickness is XF, right? This, right, plus EL, and this thickness is Tox minus XF, right? So this can, I could write down as XF EU minus EL plus EL times Tox, right? And EL, yeah, XF right. Okay, so okay, so what is EU minus EL? So U minus EL is nothing but DU minus DL divided by EX plus this is EL to EX, right? So DU minus DL is nothing but du QF, right? So XF times QF divided by X. EL is QSI, right? So I could also write down this as QF Tox divided by epsilon ox. Anyway, so let me write down, right? QF divided by Cox plus QSI divided by C oxide. So here you see your oxide voltage drop in the oxide. Now this changes with QF, right? So it also depends where this QF is located, right? So if XF equal to TX, right? If they are located at the interface that we have done right earlier, right? So your oxide voltage drop will be QF by Cox plus QSI by Cox, right? Right. But if XF is 0, that means if your charge is located at the metal and oxide interface, so that means your Vox, there will be no effect on Vox, right? Right. So your oxide, because see, because some charges in the oxide will change the electric field in the oxide, right? So since the electric field in the oxide changes, your oxide drop, voltage drop across the oxide will change. Since the voltage drop across oxide changes, your threshold voltage will change, right? So your threshold voltage in this case, right? Your threshold voltage is Vox, right? So this is QF by Cox plus QSI by Cox is 1 by Cox root over 2 epsilon Si QNA times root over 2 psi b plus 2 psi b, right? And this is not QF, so basically I have to do this XF by T oxide, right? So so this is just a general equation. Depends upon where your charge is located. So if your charge is located right at the metal and silicon dioxide interface, then your XF will be 0, and this term will not be there, right? Right? This term will not be there. But if this charge is located at the interface of silicon and silicon dioxide interface, then your XF will become Tox. Then whole amount of your QF by Cox will be added to the threshold voltage. But keep in mind, again here this QF is negative. If QF is positive, then your threshold voltage will be minus QF by Cox times XF into Tx. So this will be right, and 1 by Cox QNA root over 2 psi b plus 2 psi b, right? So these are the effect of charges in the oxide. So charges in the oxide will also modulate your threshold voltage. So threshold voltage will also depend on the charges in the oxide, right? Okay, any questions here?
Sir,
Yeah.
if my charge is not just distributed in a line, what if it is distributed uh, throughout the oxide?
Yeah. So then you have to, so basically what is generally done, you have to find a effect. So let's say see, this is where you know the location of the charges, right? In the most of the time you do not know the location of the charge, right? So if you do not know the location of the charge, but if you know that magnitude of charge is negative, your threshold voltage will increase. If the total magnitude is positive, your threshold voltage will decrease, right? But you cannot really actually mathematically figure it out, okay, what should be my threshold voltage, right? Unless you know the exact location of the charge, right?
Yes, sir.
Okay, so just keep in mind, the positive charges in the oxide or interface, right? Positive charges in the oxide or interface will reduce your threshold voltage. Negative charges in the oxide or at the interface will increase the threshold voltage, and this will be governed by the equations that we have derived, right? Okay. So, and this change is because of change in oxide voltage drop, right? Because the moment we have some charges either at the interface or inside oxide, your electric field in the oxide changes. Since the electric field in the oxide changes, your voltage drop in the oxide will also change, right? And because of this voltage drop in the oxide, whether it is higher or lower, then the threshold voltage will change accordingly. Okay. And another thing, what we have assumed in the beginning, when I started our MOS transistor discussion, that your phi m, your metal work function, is equal to semiconductor work function, right? So this is where we started, right? Your metal work function is equal to semiconductor work function. But it may not be true, right? So if you think of a silicon, right, think of the transistor that you have started with, right? In 1980s, when MOS transistor, means late 1970s, 1980s, when MOS transistors are fabricated. So people are using aluminum, right, as a gate, right? Aluminum as gate, right? Gate material, right? Gate metal, right? So if you know aluminum has a work function of let's say around 4.1 electron volt, right? So aluminum has a work function of around 4.1 electron volt. Now, if you look at silicon, right? So when I talk about silicon, we are talking about p-type silicon, right? Because our substrate is p-type silicon, right? So for NMOS case, your substrate is p-type silicon, right? For a p-type silicon, what is the work function? What will be the work function of a p-type silicon? So what is the definition of work function? Work function is nothing but the energy difference between vacuum level and Fermi level, right? Because so this is means in a simpler way. So how much energy we require to extract one electron from a metal, right? So that means we require that much energy to have them to become means to make the electrons in the metal free, right? So this right. So this is nothing but the energy difference between vacuum level and Fermi level, right? Assuming that at Fermi level we have electrons, and the vacuum they will become free. So this much energy they need, electrons need, right? So that is the definition of the work function. But for a silicon, again, right? So this is a semiconductor, right? So and so this if this is a p-type silicon, your Fermi level for a p-type silicon is the electron affinity, right? So if I'll tell you, so this is my vacuum level, and we earlier we had done. So this is your conduction band, this is your valence band, and this is your electron affinity. Electron affinity is always between conduction band and vacuum level. Then I have my intrinsic energy level here, and in this p-type silicon, my EF is somewhere here, right? Very close to EF is close to valence band, right? So if I want to find the work function of the silicon, right? So your phi s, in this case phi silicon, is your electron affinity plus Eg by 2, right? So this is my Eg by 2 plus this number, right? So this is nothing but your psi b, right? And this is Eg by 2 Kt by Q ln Na by Ni, right? So if right, so if Na is very high, your Fermi level will be close to the valence band, right? Right. So if Na equal to Ni, right, then your this psi b will be 0, right? If Na equal to Ni, that means your Fermi level will be right at the intrinsic level, right? So your psi b will be 0, right? So this is and if you calculate, so for a silicon, this is 4.05 electron volt, because you know the electron affinity of silicon is around 4.05 electron volt, and this Eg by 2 is 0.56, right? And this is something around 0.4 volt, right? If I take 26 millivolt ln, if I take 10 to 17 by 10 to 10, right? Your psi b will be 0.41, right? zero point 0.4 something, right? So around 0.4, around 0.41 volt, right? I don't remember exactly, right? So if you do that, so 4.05 plus 0.56, right? So you could 1, 6, 7, 12, 8, 5, 10, right? Yeah. So 5.02 electron volt, right? So if you see, the silicon work function is around 5.02 electron volt, right? At this 10 to 17 doping, right? So again, the work function of silicon will change with the doping, right? So for 10 to 17 doping, your phi si, the work function of silicon is 5.02 electron volt, but the work function of metal, we are using aluminum. Let's say we are using aluminum. This is around 4.1 electron volt. So your phi m is not equal to phi s, right? So phi m, if you see, your phi m is not equal to phi s, right? So what will the effect of is if your phi m is not equal to phi s? Because we started in the beginning, when we started your MOS transistor, we started that, okay, let's assume that work function of the metal equal to work function of the semiconductor, but that is not the case, right? So what will happen? Anybody?
Our bands won't be flat at 0 voltage.
Yeah.
Static will be.
Yeah, but okay, let's not go to the bands flat or not. So if you think of two metals, right? So let's say I have metal 1 and this is phi m1, and I have metal 2 with a work function of phi m2, right? So if I if um, if I put them together, right? If you bring them together, so both the metals, right? Let's say metal 1, metal 2, I means I bring them together. So what will happen? So let's say your phi m1 is less than phi m2, right? So work function of metal 1 is less than work function of metal 2, and I'll bring them together. So if I bring them together, what will happen, right? So if phi m1 is less than phi m2, right? So so actually the electrons will always want to move to the lower work function metal, right? Higher work function metal, because if you see, if your vacuum level is constant, vacuum level is flat, right? So if you think of metal, metal 1 is here and metal 2 is here, right? So you see, the electrons at the metal 1, electrons are metal 1 will always want to go to electrons in metal 2, because the band in the metal 2, because the electrons want to go to the lower energy level, right? So so that's the reason why, if there is always a electric field in this direction, right? So because I don't want any current, because in the equilibrium condition I don't want any current flow, right? So automatically what will happen, there will be electric field developed. So if you bring these two metals together, so there will be electric field which is always from the low work function metal to the high work function metal, right? So so that is so there will be electric field. So basically when you bring them together, there will be an electric field from low war function metal to high war function metal, right? Okay. So right, so here, so this electric field is internally double. This is like a built-in electric field, right? Like we have discussed in the PN junction, right? So this built-in electric field will prevent the flow of electrons from M1 to M2, right? Okay. So similarly, if I come back, right? So let's say I have metal with 4.1 electron volt and I have semiconductor with 5.02 electron volt, and I am bringing them together, right? If I'm bringing them together, so there will be a electric field from metal to the semiconductor here, right? So if I think, right, so what I'm telling here is, anyway, if I have my uh, transistor, but let's say this is my metal, and let's say this is aluminum. So this metal is aluminum, right? So and this is p-type silicon here, right? So the moment I have that, right, the moment I'll not apply any electric field, even if my gate voltage is zero, I'll not apply any. Means basically I'm not applying an external voltage, right? But since this work function of aluminum is less than work function of silicon, so there will always be an electric field in this direction, because there is an electric field from lower work function metal to the higher work function metal, right? So since there is an electric field, and this strength of this electric field will depend on the work function difference, right? So this electric field is proportional to phi m minus phi s, right? So right, so basically if the difference between the work function is higher, your electric field strength will be higher, right? So this electric field, since there is an electric field from metal to the semiconductor in this case, so there will be some charges, right? So there will be some charges because there is electric field, so your silicon cannot be charge neutral, and so there will be some charges, right? So what does it tell you? That it tells you that even if I am not applying any gate voltage, because of the work function difference, I have already some negative charges here in this case, right? So if I apply means Vg equal to 0, that means this is not, even if so Vg equal to 0 volt, I have already some negative charges, right? So what does it mean? since I have already some negative charges at V is equal to 0, that means I have to apply very few, means less gate voltage to invert the surface, because I already have some electric field at V is equal to 0, right? So to invert, I need some more electric field, and then I could apply some more gate voltage to invert the surface, right? So that means the threshold voltage in this case will be lower, right? Since so if phi m is less than phi s, then your threshold voltage will be lower, right? Right. So what do to be clarify? Let's say when I have phi m equal to phi s, right? Let's say your MOS transistor has a threshold voltage of VTH1, right? And phi m is less than phi s, then I have some VTH2, right? And phi m greater than phi s, I have VTH3, right? I have three MOS transistors with these conditions, right? So your VTH2, what I'm telling is VTH2 is will be less than VTH1, will be less than VTH3, right? So I hope you understand, because in this case, uh, here, right? So there is already electric field from gate to the substrate, even if I have not applied any voltage, right? But in the other case, right, when phi m greater than phi s, right? So when phi m greater than phi s, I have electric field from substrate to the gate, right? The moment if I have electric field from substrate to the gate, right? So that means my surface is accumulated. I have holes here, right? I have holes at the surface, right? So to invert, I have to apply more gate voltage, right? So so your threshold voltage 3 will be more than threshold voltage 1, will be more than threshold voltage 2, right? And that's the reason when you look at VTH, basically your VTH here. I had derived some, right? So I have derived this XA by Tox times QF by Cox plus root over 2 epsilon Si QNA root over 2 psi B Cox plus 2 psi B. So this is my threshold voltage. So now I have to add something called phi ms, right? So this just tells you the voltage the work function difference, right? And this phi ms, right? So you could see, so this phi ms is nothing but the work function difference. So if your phi ms is negative, that means your phi m is less than phi s, your threshold voltage will be low, right? If your phi ms is positive, that means phi m is more than phi s, your threshold voltage will be higher, right? So if I look at this equation, so these two terms are always there, right? These two terms is my intrinsic transistor, right? And if I add these two terms, right, because is uh, this is coming because of the non-ideal case, right? So this phi ms and xf by Tox times qf by Cox, right? So this total I could write this as the flat band voltage, right? So these two terms is called flat band voltage plus your okay, let me write down on the next page. So please ask me questions if you don't follow me, right? Um, so your threshold voltage will be the flat band voltage plus 1 by Cox root over 2 epsilon Si QMA root over 2 psi B plus 2 psi B, and your flat band voltage is nothing but your phi ms, right? Phi ms plus uh, let's say you have some charges at the interface, so QIT by Cox, and if you have some charges in the oxide, then this will be XF by Tox times QF by C oxide. Right? So uh, this is called the flat band voltage. So I need this voltage to make sure that your band structure is flat, right? Means there is no electric field, right? Right. So that's why this is the significance of the flat band voltage. So so if the flat band voltage is 0, where we started assuming that, let's say, both the phi m equal to phi s, there is no charges. So it's a silicon is ideal, your silicon dioxide interface is ideal, your oxide is ideal, then your flat band voltage is 0, right? That right. But the moment, if you look at the practical transistors, so there is a finite difference between metal and semiconductor work function. So that will give you electric field. So you have to negate that, right? So basically you have to apply some additional voltage to the gate to make sure that your, even if you have 5 ms, so your bands are still flat, right? Right. Similarly with this QIT and QF, right? So these three terms, we call it the flat band voltage. And uh, right, for the silicon, for a NMOS transistor, right? So if you look at the NMOS transistor, right, your 5 ms, right, is okay. So before we go there, before I go there, so I just want to tell you that in a in a typical MOS transistor nowadays, so in a typical MOS transistor, um, right, your gate is made of polysilicon, right? So your gate is made of polysilicon because we started with metal, right? We started with aluminum, right? But aluminum cannot withstand very high temperature, right? So we move to polysilicon because polysilicon, so this is highly doped silicon, right? So this is silicon but highly doped. So for a NMOS transistor, your substrate is p type, but your gate is n plus polysilicon, right? So your gate is n plus polysilicon, right? So this is your NMOS transistor. So if in this case, if I want to calculate my phi ms, right? So because your gate is made of n plus polysilicon, your body, your semiconductor is p type substrate, your p type semiconductor. So your phi ms will be nothing but so this will be so phi. Okay, I could do with phi m minus phi s. Phi m is the work function of the n plus polysilicon, which is nothing but the electron affinity, because this is n plus polysilicon and very highly doped n plus polysilicon. So your conduction band, your Fermi level is inside the conduction band, right? Mostly close to the very close to the conduction band, right? So your phi m is nothing but your electron affinity. And for a p-type semiconductor, this is electron affinity plus Eg by 2 plus Kt by Q ln Na by Na, right? Right. So this is nothing but your phi ms is nothing but minus Eg by 2 minus Kt by Q ln Na by Ni, right? And this is nothing but minus they calculated minus 0.56 minus 0.41, right? For this is for Na of 10 to the 17. So this is around minus 0.97 electron volt, right? So your phi ms is negative. For a typical NMOS transistor, your phi ms is minus 0.97 electron volt, right? So that means you have to apply, because you have in the beginning you have minus 0.97, there is electric field from gate to substrate. So to make the bands flat, I have to apply this positive 0.97 electron volt, right? So I have to apply positive Vg, right? Uh, okay. If I want to, let's say, if I want to calculate the threshold voltage of NMOS transistor, so this will be flat band voltage. Right. So let's assuming there are no charges. Assume, because I have to make it simpler. Assume your QF is 0 and your Q interface 0. So then this will be just 5 ms. BFB is 5 ms. This is minus 0.97 electron volt, right? Right. and then if you calculate this thing, so this will be I had done this calculation. So your psi b, so let's say Cox equal to Eox by Tox, assuming Tox to be 3 nanometer. So you could calculate this, right? 3.98.854 into 10 to minus 14 farad per centimeter into 3 into 10 to minus 7, right? So this is how we'll calculate Cox. And assuming, I mean, putting Na equal to 10 to 17 per centimeter cube, right? Uh, so your this term will be 0.146, and this term is around 0.8838, right? 2 psi b, right? 2 psi b is 2 times kt by q ln na by ni. So with this you'll get right. So with this you'll get um, how much? Let me calculate. 0.838 plus 0.146 minus 0.97. So this will be around 0, right? So this is 0.014, right? Volt, right? So you see, for this condition, right, your threshold voltage is coming out to be um, 0.014 volt, right? Is around 14 millivolt. Your threshold voltage of the transistor for this condition here, threshold voltage of the transistor is around 14 millivolt, right? So this is how you calculate the threshold voltage. Again, if you are given the charges, if you are given fixed charges and the interface charges, you could also again calculate, right? So if so your this unit should be per centimeter square, coulomb per centimeter square, right? So coulomb per centimeter square. If the charges are given, then qf by cox will be added, right? And qf by cox and q into by cox will be added to these equations, right? Okay, so this is the typical transistor. So now, so what you have done till now is for an NMOS transistor, right? But for a PMOS transistor, right? For a PMOS transistor, when we are talking about a PMOS transistor, um, the PMOS transistor, what is generally done, and your source and then are P plus, uh, your right, right, and your gate is P-type polysilicon, right? So your gate is p-type polysilicon. So this is generally done to make sure that your VTs are symmetric, right? So in any digital, if you means basically what we want, right? So we always want our NMOS transistor VT is equal to PMOS transistor VT, not equal to. That means if your NMOS transistor VT is 14 millivolt, your PMOS transistor VT should be minus 14 millivolt, right? They should be complement each other, right? So they should be exactly equal but complement each other, right? So that means if one VT is 14 millivolt, the PMOS VT should be minus 14 millivolt, right? Okay, so here you see when your you have to apply negative gate voltage to invert it, right? And your surface potential will be negative, and also your voltage drop in the in the oxide will also be negative, right? So you could also write Vg equal to Vox plus 2 psi b at sorry, Vox plus psi s. But keep in mind, in this case, in case of PMOS, your Vg is negative, you apply negative voltage. Since your electric field is from bulk to metal, right? So your oxide voltage drop is negative because your electric field direction is changed. So your voltage drop will be negative, and psi s will also be negative, right? So right, but you could still use the same equation, right? And threshold voltage will still be 2 epsilon Si Q N D because your this is N type substrate. Um, root over 2 psi b plus 2 psi b, right? So here your ND, your threshold voltage will be negative because your 2 psi b is negative here, right? Because your surface potential. Right? So if you know the doping of the substrate, right? If you know the doping of the substrate, that means if you know the ND, if you know oxide thickness, right? Then you just calculate VTH simple by this formula and add a negative term, right? So and when you're talking about work function, right? So your flat band voltage for a PMOS transistor will be again 5 ms, right? But in this case your 5M is more than 5s because your metal, your gate is p-type polysilicon. P-type polysilicon. So if I do the p-type polysilicon, so your this will be x plus Eg, right? So your work function equal to because this is a p plus polysilicon is electron affinity plus band gap, right? And your phi s your silicon work function, this is n type substrate, so your electron affinity plus Eg by 2 minus Kt by Q ln Nd by Ni, right? Right. So for a p-type silicon, you see your formulable will be somewhere here, right? Ec, Ev, and here this is your Ei, right? So this is your vacuum level. So your work function is this is your x, right? Electron affinity. Then this is Eg by 2. Then you have to minus Kt by Q ln Na by Nd, right? Ln Nd by Ni, right? Right. So so here your this will be Eg by 2 plus Kt by Q ln Nd by Ni, right? So this is your flat band voltage for a PMOS transistor, right? And if you look at the flat band voltage that you have calculated for NMOS transistor, this is minus Hg by 2 minus Kt by Q ln Ni, right? So so that's the reason your flat band voltages are almost same but opposite magnitude, right? So here in this case this will be 0.56, and if I take Nd equal to 10 to 17, then this will be equal to 0.41. So this will be 0.97 electron volt, right? So your work function, your flat band voltage will be 0.97 electron volt, right? But a positive 0.97, unlike your minus 0.97 which are calculated for NMOS transistor, right? So NMOS and PMOS, there is not much difference. If you choose the same substrate doping, your flat band voltage will be same but in the opposite, right? Magnitude, right? Okay, so then you could see the threshold voltage. If you calculate the threshold voltage, you will see that you will get minus 14 millivolt, right? Because you have to apply plus 0.97, right? And this will be again 2 psi b. 2 psi b will be minus 0.41, and this will be minus point whatever I have calculated, minus 0.146, right? Right. So if I do that, right, not 418. 38, right? So when you do that, it will again be minus 14 millivolt, right? So for NMOS transistor and PMOS transistor, if you choose the same doping, right? Same doping means if the N substrate doping is equal to P substrate doping, and your oxide thickness is same, then your devices will be exactly symmetric. That means symmetric means, so if your NMOS transistor gives 14 millivolt VT, your PMOS transistor will give say minus 14 millivolt VT, right? So that's the reason. Means when you're in the CMOS technology, we want to make sure that your NMOS PMOS transistor have similar VT. So why similar VT? Because similar VT we need because we want to means basically we equate the currents, right? So if you have done the inverter, right, so you equate the currents, right? So basically you don't want, if you think of a inverter, um, if you think of a inverter, right? So if you think of an inverter, so inverters basically we are charging this capacitor. So once one case through the PMOS transistor, other case through the NMOS transistor. So other case we discharge the NMOS transistor through the discharge the capacitor through the NMOS transistor. But we want to equate these currents. We want these currents to be same, right? One case we discharge, right? So these two currents to be same, right? These two currents will only be same, right, when my threshold voltages are same, assuming their mobilities are same, right? So we'll come to mobility, their mobilities are also not same. So we have to make sure that this current is equal to this current is equal to this current. So basically we always start with symmetric VT, right? So if you look at the design manual, so you'll find that the NMOS transistor VT is very close to PMOS transistor VT, a threshold voltage, right? Okay, so this is all about threshold voltage. So if you have any questions, you could ask me. So what we'll do is we'll take because we have to take another half an hour. I need another half an hour today. So we could take 5 minutes break, and then we could start again, right? Okay, any questions? Otherwise, we'll take 5 to 6 minutes break at this point.
Sir,
Huh.
sir, but in actual condition, means PMOS and NMOS VT is not equal. That's why the case.
No, but they when we try very hard to make sure that they are equal, right? So in the technology, when we are doing CMOS technology, means when you design our transistor, we make sure that their VTs means is almost same, right? So but keep in mind, right? So means we try hard, but there is because if there are some charges, right? So charges will be positive all the time, whether it is NMOS or PMOS. If I have some charges in the oxide, that charges will be positive. That will not be positive for NMOS and negative for PMOS, right? That charge will be same, right? So if I have single on positive charge, then there will be some VT difference between NMOS and PMOS transistors, right? But our goal when you device design, right, for a particular technology, so our goal is to make sure that NMOS transistor VT and PMOS transistor VT, they are symmetric, right? That means if I have minus 400 millivolt for the PMOS VT, your NMOS VT should be 400 millivolt, right? But there will be some difference, right? We cannot make them equal all the time. But there is not huge difference between NMOS VT and PMOS VT.
Yes.
All right, so we'll take 5 minutes break. I'll come back in 5 minutes.